Hello everyone. In this video, I'll share with you how to use BrainCog, a brain-inspired cognitive intelligence engine, to implement N-Omniglot, a large-scale neuromorphic dataset for future learning. The success of deep learning is attributed mainly to the common used datasets for the benchmark like ImageNet and COCO. DVS simulates the human visual nervous system from a specific perspective and a level abstraction, which allows spiking neural networks to take full advantage of the temporal information provided by such sensors. To facilitate the development of brain-inspired artificial intelligence, especially the spiking neural networks, several neuromorphic datasets have been produced using dynamic vision sensors. For example, N-Omniglot, N-Caltech 101, and decode are obtained by capture images or cameras movements from traditional classification datasets, avoiding the corruption of the original image information during encoding. Besides, more researchers acquire data from natural environments, such as gesture and N-cars. However, the existing datasets have very low temporal correlation and could not fully reflect and exploit the temporal information processing capability of the spiking neural networks. Their characteristics are shown in the table. In addition to sparse coding to reduce energy consumption, rapid learning of new concepts from a few samples is one of the essential capabilities of the human brain, but this remains an open problem in spiking neural network-based machine learning. To address this issue and bridge this gap, we propose the first new neuromorphic dataset for future learning, the N-Omniglot. The original Omniglot dataset is widely used in future learning. The N-Omniglot consists of 1,623 handwritten characters from 50 different languages. Each character has only 20 different symbols. It's usually considered a static text image and ignores the rich temporal information in the written process. We know that the spiking neural networks is still in its infancy in neuromorphic future learning. Although we have constructed an Omniglot, very few existing algorithms are suitable for this task. All experiments have been performed on both N-Omniglot and encoded Omniglot to demonstrate the difference between them. As shown in the figure below, we treat static images with person and constant coding. Since the device camera for acquiring neuromorphic data has a high temporal resolution, the excessive long time access is a huge burden for the current clock-driven spiking neural networks algorithms. Therefore, we process the event data with OR operations and firing rate. To demonstrate the effectiveness of N-Omniglot and the potential to provide new challenges for training spiking neural networks algorithms, we conducted experiments on 4 SN algorithms, including adaptations or SN versions of 2 general classification pattern classification methods and 2 future learning algorithms. N-Omniglot dataset is more sparse in the spatial dimension, and the data is less similar in temporal dimension than the static image or person coding-based inputs, which brings new challenges to spiking neural network learning. It is crucial to improve the ability of spiking neural network to extract more important spatial temporal features. Therefore, an Omniglot can be considered as an effective, robust, and challenging neuromorphic dataset for developing future spiking neural networks. In the BrainCog framework, we provide a variety of data interfaces for an Omniglot. N-Omniglot file provide basic data passing functions and convert raw 84 files to NumPy files to avoid duplicated raw data processing. In addition, we provide data interfaces for direct classification, meta-learning, and metric-based visual learning, which you can call as easily as you usually would with other datasets. Test case can be found at this net. If you have any questions, feel free to email us and welcome to cite our work. Thank you all.